the record button. I can. Okay, so you ready to go, Mike?
Yeah.
All right. So thanks everyone for being here at this week's seminar. I want to introduce this week's speaker, who I've known for probably going on 30 years now.
Don't say the date. Don't say.
I'm not saying the date. I'm not saying the date.
Makes it sound old.
They know me. They know it. They know the reality. But I want to introduce Mike Interbartolo, who's our seminar speaker for this week. Mike is originally from the Boston area and received his bachelor's degree in aerospace engineering from the University of Michigan, and went on to get his master's degree in mechanical engineering from George Washington University. After that, he spent the last 25 years at NASA in a range of roles spanning the everything from space shuttle missions to the Orion Avionics power and software, Mars ISRU, with lots of acronyms, definitely a government job here. Field demo project manager, as well as business development and partnerships with industry. The project he's currently working on is really exciting. It's the Crew Compartment Office and the Human Lander Systems Program. The goal being to help land the first woman and the next man on the south pole of the moon, coming up in just a few years. So
My clock says 1,200 days.
1,200 days today.
Well, we have a rough
1,200 days.
We have 1,200 days left to get it done. Approximately.
Very cool. So with only 1,200 days left, I'm very glad that you were able to come and spend an hour with us. So with that, hand the floor over to you, and look forward to your talk. So thank you.
Excellent. Thanks for inviting me, Steve. It's good to see you again. So I'll start off with a little promo video on NASA first. Hopefully this works good.
Roger the pledge. 7, 6, 5. Roger. You're looking good. 3, 2, 1.
We are the explorers. We have a need to find what is out there. It is a drive inside each and every one of us. The drive to wonder, to push the boundaries, and to explore. We expanded across our lands, settling new frontiers. We took to the oceans and learned that we could cross treacherous expanses in the pursuit of discovery. And then we took to the skies and flew. But that wasn't enough. We left the planet and redefined what was possible. We flew in space. We walked in space. What once was a melodramatic flight of fantasy became reality. Then, a new generation of spaceships captured hearts and minds for 3 decades and helped build a castle in the sky that is our lasting home in space. We have always looked up. For centuries, we wondered what was on the other side of the sky, and we have begun to answer that question. We have learned that all the exploration humankind has achieved is only a beginning. Right now, men and women are working on the next steps to go farther than we have ever gone before. New vessels will carry us, and new destinations await us. Everything we have ever accomplished leads to this moment in time, where exploration will now take us to the planets and the stars. Our nearest neighbors in the night sky have beckoned us, invited us, dared us to reach for them. We are the explorers. Throughout our history, we have taken both small steps and giant leaps in that pursuit. Our next destination awaits. We don't know what new discoveries lie ahead, but this is the very reason we must go.
So hopefully the audio came through on that. You might recognize Peter Cullen, Optimus Prime from the original Transformers, did the narration of that, which is always pretty cool. So Steve mentioned a little bit about my career path. Again, I was born in the Boston area. I went to the University of Michigan for my bachelor's degree, and then I went right into grad school. Back then, there wasn't many aerospace jobs. In the mid 90s, there was a lot of my colleagues at Michigan ended up going into the car industry, and I always wanted to work for space programs. So I decided to go to George Washington University, which was really close to the Goddard Space Flight Center there in Maryland. Unfortunately, the summer before I started there, the co-op program got canceled at GW. So I was kind of at a loss on how to get my foot in the door. So my dad's like, well, why don't you just try going volunteering? So I called up the front desk at Goddard, and I forget how I got routed to the branch I got routed to, and said, I'm an aerospace engineer. I'm in grad school at GW. Could I come work there and get some job experience while I'm going to school at night? And it took a couple months. There was the government shutdowns in there a couple times, and I think legal was trying to figure out if he dies on site, are we responsible for his body, or do we just throw it over the fence to the Baltimore Washington Parkway and never hear from him again? But so I started in February of 1996 at Goddard Space Flight Center. It was like an unpaid internship, basically. They moved me around to different projects to get different experience and see how I fit there. As a GNC analyst, working mission timeline, some hardware support for some small payloads that flew on the space shuttle, as well as different satellites and stuff that they were building. And then a year later in 97, I was graduating, and I sent a letter of resignation up to the center director to resign my status as a volunteer. I was basically fishing for a certificate of appreciation for 16 months of working for free at that point. And the center director and I had had a little history a few months before during a reorg of going back and forth over email. And so he recognized the name and found a way to get HR to hire me on as a term employee. So I was a NASA employee, but I was only on a 4-year contract at that point, with the hope that they would be able to convert me to permanent before that 4 years expired. And then in 98, the Johnson Space Center was ramping up their flight control teams because they were about to start construction of the International Space Station. So they needed both the shuttle flight control team and the space station flight control team. So they had moved some of their experienced shuttle folks over to station, and they were trying to backfill the shuttle folks. And so they came up recruiting to transfer down. And so I jumped at the opportunity to work on the space shuttle program. And so I transferred down in 1998 to the Johnson Space Center to work as a shuttle flight controller. So my first position was ascent entry control. So that was during launch and landing of the space shuttle. It was in charge of basically the space shuttle main engine gimbals, the solid rocket boosters, thrust vector controls, the aero surfaces. So basically during launch and landing, that the shuttle knew where it was going and how it was going to get there, that the pointy end was always pointed up, or the glider was going to be able to glide back to the runway, though it really is a falling brick, as we like to say. But so it was basically just so the shuttle could get into orbit or back to the runway. That was the first position. So I worked 7 missions at that position. I also got certified at ascent entry sensors. So that's the inertial measurement units, the microwave landing system, GPS, some of the other nav aids, again, for the shuttle going up and down, and then orbit back room, and then orbit front room. So the only position I didn't get in my discipline was ascent entry front room, which I moved on to another management position before I got certified there. So all told, I worked, I believe, 13 missions as a flight controller, and then another 14 as part of the mission management team. So I was sort of a liaison between the mission control team and the orbiter project office, who managed the actual hardware on the space shuttle vehicle and all that. So it was a great career in mission control. So this is one of the pictures. We always took a team photo pre-mission before the launch with the flight director, and then usually the crew would come over after their last sim before the mission. So this is just a small portion of the team. So in the room here, this is the shuttle flight control room. Each position that sat in here would have several people in a back room position. So that was the ascent engine control was a back room. So we didn't sit in this room here. We were off in one of the back rooms behind. supporting the front room position that was in here, and they would coordinate within the room to the flight director, who would tell the Capcom, who would call up to the crew and stuff like that. That's sort of the hierarchy of how things go and stuff like that. So these are just a few pictures from my time in mission control over the years. So we did really build with the space shuttle, because we had that large up mass capability. The space shuttle payload bay could basically take a school bus worth of payload up there. So we built the International Space Station. The first two pieces went up in 1998, November. And then about 2 years later, the station had enough capability to support 2 crew members living on it permanently. So some of you may be actually young enough to never known when at least 2 people have always been living off the Earth at the International Space Station. Typical shuttle would have 7 crew members. Nowadays, the space station has 6 or 7 crew members. So at any one time, I think the most we had in space, due to crew rotations with the shuttle and Soyuz up there at the same time, they weren't all docked together at the space station, was about 15 people in space at one time, between the shuttle, the space station, and then a crew coming up on a Soyuz and stuff like that. So that was the castle in the sky we had the great pleasure of building over the years. And there's some good apps out there called ISS Flyover, I think, and you can get alerts on when it's going to fly over your location at night, what angle of the sky to look at in what direction, and you can see it. And it's pretty bright because of all those solar panels you have on it. It lights up the night sky pretty much. So if you look at that bottom right picture there, the space station, from one end of the solar rays to the far end of the truss to the other end of the solar rays, that's about a football field, American football, not soccer football. And then each of those solar ray panels is about a basketball court. So you get a sense of scale there in size. So this is the mission control for the ISS flight control room. Because the ISS is just going around in orbit, it's not as dynamic in terms of coming through the atmosphere and stuff like that. And there's downtimes on the crew weekends and stuff like that. The room flexes in terms of how many people are in the flight control room at a time. On the weekends, when the crew is during their off-duty time, you're looking at potentially as little as 4 people in there. And that really shows the advance of the computer technology. When I worked in the shuttle program, it was colored screens, which was a big deal. In the early shuttle days, it was still the old vacuum tubes and mainframe computers that were run out of the basement that were the same computers that ran for the Apollo era that went to the moon. So it wasn't until about 1995 that the shuttle flight control team moved from mainframe computers and vacuum tube displays to DEC alphas, so a little bit more distributed architecture. We still had big CRT monitors. Now you can see there's all flat screens there. So when I started as an asset entry flight controller, I was probably doing, because of the computational power of the displays of colors and plots and all that, about what 4 people would have been doing in the first shuttle missions for that same position, because you had, you needed more eyes on the screens to watch plots, printing out on strip charts and other things, or zeros flipping to 1 and stuff like that. Whereas with color, you can have sort of in your scan pattern, see a number turn yellow as sort of a warning to catch your eye, so that then you can kind of zone in on it and see, oh, that's trending in the wrong direction or something like that. The pressure's building up in the hydraulic unit for the main engine TVC number 1 on the left engine or something like that. So with color and plots and limit managers and other things like that, the flight control team has more capabilities now, and so they can go down to reduced numbers. During dynamic phases or critical operations, like a crew out on a spacewalk or a visiting vehicle coming up to dock, the room will be more full and stuff like that. But it flexes on how much support it needs depending on the dynamics of the event. So the ISS FACS, for those who don't know, travels at 17,500 miles an hour, which means you orbit the Earth every 90 minutes, seeing 16 sunrises and sunsets per day. You see temperature swings between about plus 250 to minus 250, depending on the shade and the time of year with the orbit and the beta angle to the sun and all that. The pressurized modules, think of it as about 2 747s in terms of interior volume. And again, the truss segment from wingtip to wingtip of the solar rays is about a football field in length, and the solar rays are about a basketball court each. So it is green energy. It's all solar powered for the sunlight, and then battery powered when it's in darkness for those 45 minutes. So those solar rays have to obviously be charging up the batteries for those 45 minutes before they go into darkness, as well as powering the vehicle. And We're not completely closed loop, but we do have a saying that today's coffee is tomorrow's coffee. So we do recycle the urine on board, and the crew says that it actually tastes really good, that it's the best tasting water that they've ever had. Now, granted, they've been stuck in space for 6 months, and the interior of the space station smells like a dirty locker room. So, their taste buds are a little different than here on Earth anyway. But it is very clean water. It's basically pure oxygen and hydrogen put together as water. So in November 2009, after working 27 missions in mission control, again, some of those as flight controllers and then some of those as part of the mission management team, I moved on. I was asked to be the Orion program's avionics, power, and software deputy of the office. The head of the office was an engineer, and he wanted sort of that mission operations perspective and background to sort of, counter his gaps in knowledge and his different perspectives, to sort of challenge him, to make sure between the two of us that we were getting the complete picture as we were building up the Orion spacecraft. So that's a look at what the Orion spacecraft is down in the bottom left. And then about a year after I took over, moved over to Orion, we went through that cancellation in February of 2010, and then trying to figure out what the path forward was for Orion after that. So I moved over as a Mars project manager for Marco Polo. So it was a 3-meter diameter hexagon, if you will. I think we ended up going with an octagon eventually, but and it was basically a lander that was going to process Mars atmosphere and Mars soil with enough throughput that it could provide a crew of 4 some of their life support and needs during a Mars mission. So the Mars atmosphere is very thin, but it's carbon dioxide rich. So you can take that carbon dioxide, run it through a Sabatier reactor with hydrogen, and create methane and water. So we had that atmospheric processing module there that would freeze the carbon dioxide out of the very thin atmosphere and then convert it into water and methane. And then we had a soil processor, because the Mars soil, depending on where you land, has between 5 and 18% water content in the soil. It's dirty with perchlorates and all that, but it's still water that you can dry off in the soil processor, such that you bake that water out of the soil, you capture that water, you run it through a water cleanup system to get rid of all the perchlorates, and then you can either electrolyze some of that water so that you can then run a fuel cell for nighttime power, such that you had power for keep alive and whatnot during the night, or you have that water for the crew to drink, or oxygen for the crew to breathe, or methane and oxygen, or hydrogen and oxygen for your rocket propellant, or again, the fuel cell for a rover, or just nighttime power and whatnot. And then, so that went through a couple of cancellations over the years. I guess I've been kind of cursed since I left flight control, but the agency has pivoted back and forth between Mars and Moon and Mars over the years. So the Marco Polo sort of never got fully built up, and it was actually going to do a field demo in Hawaii because of the soil there is very reminiscent of the Mars soil. I think that was one of the reasons they got me to work on it, was because they promised me a trip out to Hawaii. But in the end, it still actually lives today. The atmospheric processing module actually was transferred down to KSC, and they've actually built that up now. And the electrolyzer is still in use at JSC to try to take that water and crack it back into hydrogen and oxygen for different experiments, to try to work on some of that closed loop life support systems. For about 6 years or so, I worked as a new business development and collaborations. So looking for external partnerships. We've done partnerships over the years. I don't know if you've seen Robonaut on the space station. That was actually a partnership between GM and NASA Johnson Space Center. GM wanted a robot that could work on the line in an automotive setting, and not the big bulky robots you always see in the cages working the line, where you couldn't have a human anywhere close to it, because if it got out of control, a human could be severely injured. So Robonaut was more something that could work side by side on the line, do some of the jobs that would potentially carpal tunnel and some of the big lifting of and moving of window panels and stuff like that. For us humanoid robots at the Johnson Space Center, it's all about the 3Ds, the dirty, the dull, and the dangerous. So anything we can offload from the crew in terms of dull stuff, like on the space station, sitting in one spot with an ultrasonic leak detector for 10 minutes, the crew has more important things to do than that, but it's important to find leaks on the space station every so often and make sure that they're not there and look for stuff like that, or dirty, like cleaning water filters, or toilets and stuff like that. And then the dangerous. So every time we go up for a spacewalk, that's the most dangerous situation we put the astronauts in. And so if we can minimize that 8 hours that they have to go out for a spacewalk by having a robonaut or some other robotic caretaker go out there and prep the sites, get all the tools set up at the work site for the crew to do the actual repair. Or eventually, when you talk about going to Mars, you're most likely sitting with your crew transport in orbit for 500 days uncrewed, and everyone's living on the surface. So you need a robotic caretaker to do any repairs on your ride home. You don't want to have to get up there at the end of 500 days and do a lot of repairs to be able to, limp your way home. You want to make sure that that vehicle to get home is in tip-top shape the whole time. So I did that for several years, looking for different partnerships. Oil and gas industry is a lot of synergy with NASA because it's extreme environments in terms of temperatures, pressures. Usually they're under crushing pressures and we're under no pressure, but it's still a lot of extreme temperature swings and stuff like that. So there was a lot of partnerships we did over the years with different industries looking for that. And the way it works is each company or university puts in money with NASA, and we bring both sides to bear on the problem and look for ways to collaborate and work on that technology so that we bring that technology to a higher level together instead of working on it separately. And then we both benefit from the advance we make in it. And now currently I am working on the Lunar Lander program, which is, again, as Steve said, trying to get back to the moon in 2024. And I've got some more charts on that. I also have had some cool special projects I've done on the side over the years. The Spacesuit Art Project was a project we started with local hospitals in the area with kids fighting cancer. And so the kids would paint on a little swath of fabric there, and they were sewn together in the spacesuits. So in that picture, you can see 3 pictures. So that's unity, hope, and courage. Hope was the first one. That is the one on the right. Courage is the one in the middle that Kate Rubins is in the background floating on the space station. So that was actually a flight suit that the kids painted on. And then Unity is the triangle one. So that one is actually with hospitals around the world. And so astronaut Nicole Stott, it was the real champion behind that. She's retired now. And so she still keeps the Spacesuit Art Project going. And they've actually, I think, created 2 more spacesuits since then, and then some other stuff with kids around the world who are fighting cancer and stuff like that. And this is, for some of the parents, this is a living memorial to their kids because the kids actually passed on, but they still have the Spacesuit Art Project as a memory of something that the kids worked on. I am a little bit geeky. This is not my geeky stuff behind me, but I do have geeky stuff at my office at work. But I do work the local Comic-Cons. So we chair some NASA panels there to talk about what NASA's doing. And we have a booth usually with some displays and stuff. So these are some stormtroopers working with the exoskeleton in between them. So that was a way to help augment the crew. Not a full up Tony Stark Iron Man setup, but something to help them with their lower body moving around, such that if after months on the space station they're deconditioned, because you do have that muscle and bone loss, that potentially as you're starting to walk on the Mars surface after that transit to Mars, which could be potentially 200 plus days, and you're slightly deconditioned, if you can build in sort of an exoskeleton to help you have that mobility right away as you get on the surface, so that you're not incapacitated for those first month or so while you're trying to recover. And then the Space Explorers is a VR series, so it's a 360 VR. The top picture there, we filmed in the White Sands Dunes in New Mexico with the rover. And this is a company, Felix and Paul Studios, out of Montreal, Canada. And so they build these cameras, and that's the camera we have on the space station right now with David St. Jacques there. It's 7 cameras around to give you a full immersive 360. And the way they position it usually is, so in the rover, the astronaut Mike Gernhardt was in the left seat and the camera was in the right seat. So when you're in the VR, you feel like you're just riding along, having a conversation with him, and he's telling you all about exploration and stuff like that. So the Space Explorer series, there's 2 episodes that are filmed here on Earth, at the Johnson Space Center, under the water in the pool, out in the White Sands in New Mexico, at SpaceX, training in Moscow as well. And it's about the astronauts talking about what exploration plans are and going forward. And now the second season is actually filmed on the space station right now with the collaboration between Felix and Paul Studios, the ISS National Lab, and Time Magazine. So the second episode just debuted on that, and it's on the Oculus platform and some of the 5G phones that have the capability to do VR. And so it's really like you're there as the seventh or sixth astronaut, depending on what time of year in terms of crew rotations there are, and you're just watching them do their work and exercise and reminiscing. There's a good scene where you're basically sitting at the table with them, and there's some astronauts floating this way, astronauts above you, because again, in zero G, you can basically sit, float anywhere in the module and stuff like that. So it really gives you an experience of going to space, what it's like to live and work in there and stuff like that. So it was a great project to work on. And actually spoke at SIGGRAPH back in 2019 about the project and stuff like that. You can find the video out there. So what is NASA doing today? Right now, again, on the space station, you've got 7 people living up there right now. This is Expedition 64. You can see the ISS is an international space station. So you have the United States, the Japanese, JAXA, the Canadian Space Agency, the European Space Agency, which makes up a couple dozen countries there. The English are, the UK is still part of ESA, that's separate from Brexit and all that. So they fly an astronaut up every so often, and then the Russian Space Agency as well. So right now, the 4 on the right-hand side there, they came up on the SpaceX Crew Dragon, and then the 3 on the left came up on a Russian Soyuz rocket. So now we do have with SpaceX the capability to actually bring up American astronauts from Kennedy Space Flight Center, and then hopefully Boeing will get their vehicle flying soon, so that we have 2 different vehicles able to do crew rotations. And then the next SpaceX Crew Dragon launch is scheduled for middle of this month, I believe. I think they keep playing with the date. It moves a little bit further back in April and stuff like that. So that'll be a little bit longer. So, you know, Mike Hopkins, Victor Glover, Shannon Walker, and Soichi Noguchi all came up on the Crew Dragon, and they will come home on the Crew Dragon later this spring and stuff like that. So we are transitioning that low Earth orbit to commercial partnerships. So we have the Crew Dragon and the Boeing Starliner as ways to regain access to the space station. After the shuttle retired, we basically were paying for seats on the Russian Soyuz until we had the commercial crew vehicles were capable. We are looking at ways to bring in more commercial utilization of the space station. For science, there is the ISS National Lab in CASIS, which runs experiments on there. So if you have an idea for an experiment, you can run it through CASIS and fly your experiment. You know, there's been medical studies that have found because of that microgravity environment, and you don't have gravity crushing the cellular crystal structure flat, you can actually see that there's embedded water molecules in certain protein structures and stuff like that that you wouldn't notice on Earth and whatnot. So Duchenne's muscular dystrophy has been some of the breakthroughs that they've made on that. And then there's Tom Cruise is talking about flying up to the space station later this year to film some stuff for some movie. I think he's even trying to push for a potential spacewalk and stuff like that. You know, Tom likes to do all his own stunts, so we'll see where that goes. And then we're also talking with Axiom and some others to expand the space station capability. So that's where that bottom picture is there. So that's Axiom's proposals for additional modules to build up on the space station. We don't really have the cargo capacity up mass these days because we don't have the shuttle anymore to bring up new modules. The Russians modules typically fly themselves up there, so we could launch Russian modules. But for all the US segment, they all came up on the space shuttle. So now with the shuttle retired, the trunk of this SpaceX Dragon isn't big enough to bring anything big up. If it's an expandable, like the beam expandable module, you could probably fit that in the trunk and then have it expand as a habitat on orbit like we have now. But in terms of a hard steel tin can, those would have to come up on something else, either fly themselves up there with some sort of spacecraft bus or whatnot. But those could potentially expand onto the space station to add more rooms, more living space, more capabilities of science. And so Axiom Space is looking to add their modules, and then eventually when the space station gets retired, those modules can separate off into their own free-flying space station. Besides, I don't want to make this all about what NASA does at Johnson Space Center and the home of human spaceflight, but there are other opportunities and other things that NASA works on. So you have the space station, which also has experiments for kids and college students to do. We have a CubeSat launcher out of the Japanese airlock there. So as low as an elementary school in Virginia actually flew a CubeSat up. I think it was one of the smaller 2U form factors there. So, it could be as small as a bread box or a box of tissues. And so that CubeSat launched from the ISS. And then there's also the spheres, which is the bronze octagon in the top left corner. That is a competition for high school software coders to do. There's a bunch of competitions beforehand, and then the final winning teams get to program 2 of those spheres modules as they free fly on the space station doing a routine and stuff like that. And then the first A in NASA is aeronautics. And so we do help out with the FAA and biofuels for airplanes or improving efficiency of airplanes, or we've done some new supersonic tests to try to do a low boom airplane to improve air travel to be faster, but without the sonic booms of old times. And then you have telescopes like the James Webb, which is getting ready to launch, hopefully, I think by the end of this year. I think they're going to get there. So that'll go up to the L2 Lagrange point, so about 1 million miles from Earth, deploy this giant array there and look back pretty much all the way to the beginning of the Big Bang and stuff like that. And you've got the Hubble Space Telescope, which is still cranking along after all these years. It's had some software glitches lately, but it's still up there running and doing great science and stuff like that. And so James Webb will eventually be the replacement for that. They do different science in terms of visual spectrum and infrared, but that is the next great observatory in terms of the James Webb. We had the Cassini at Saturn. So that's that pale blue dot with the arrow looking back at Earth there. Cassini did burn up in the atmosphere of Saturn as a disposal because of Enceladus and some of the other moons of Saturn. We didn't want to contaminate them because it does have an RTG, a nuclear power on board. And so we didn't want to contaminate any of those potential points that could have life on it. So we disposed of the spacecraft in Saturn and had just the gravity and crushing atmosphere of Saturn destroyed. Juno is still around Jupiter. And then this is actually an old picture I should have updated to the Mars 2020. So this is Curiosity in the bottom right. But we just landed Perseverance, which is basically a duplicate with some upgrades on it. And so both of them are roving around. They're about the size of a Mini Cooper. And so they're roving around on Mars doing science. The Mars 2020 is the first step in bringing back a sample return from Mars. So it'll do some science and lasers and caching of soil samples. And then eventually we'll land a lander and a retrieval robot will go out, get those cache samples, put them back in a rocket, which will launch into orbit, which will be captured by an orbiting spacecraft in Mars orbit. And then that'll return the sample to Earth and be brought back here as the first Mars sample, besides the rocks that we found in Antarctica from just ejecta over the millennium from Mars and stuff like that. And then Earth observation, that the best Earth observation we actually have is from the space station. There's a lot you can do from that lower altitude of 250 miles above. So it's from here, Houston to Dallas. I don't know what the 250 miles would be from where you guys are in North Carolina, but that observation, you get to see really the hurricanes form. And we have actually a search and rescue beacon there. There was a storm in the North Sea a couple years back where none of the search and rescue beacons, the satellites were picking up any help, and none of the search and rescue teams were finding anything. But the one beacon we had, receiver on the space station, actually found one survivor in a lone raft out in the North Sea to survive that storm. Another thing is there's more spin-offs in your world, and there's more space in your life than you realize. Memory foam actually is, from NASA. Tang and Velcro are not. We just popularized them back in the Apollo day. But you had heart pumps from the space shuttle's main engines. Dr. DeBakey here in Houston worked with NASA to take the turbopump engines from the shuttle main engines and make that into a heart pump that has helped save people's lives. The Apollo self-righting system. So when the capsule splashed down, if it splashed down due to waves and tipped over, and so it was upside down, they had airbags that would deploy and right it back up. And so that system was actually spun off as unsinkable life rafts for some of the merchant ships and stuff like that. Solar fridges, again, the space station is all about solar power, and they've come up with some solar fridges that they've deployed in remote areas such as Africa and stuff like that, that can keep medicine, temperature controlled, and it's just using solar power in these remote locations and stuff like that. The camera in most of your cell phones came from a CMOS sensor that was developed out at JPL for one of the first, I think it was Voyager. They needed a digital camera sensor on there, so that CMOS sensor was the great grandfather of what's in your camera for your selfies today. So if we had a little sticker, spin off from NASA on every item that probably spun off, there'd be a lot of stickers around that you may not realize and stuff like that. And Steve has these charts, so I'm not going to go through this one video here because I think I'm already slowing down too much. But so the big project we're working on right now is Artemis. So that is the return to the moon, the first woman and the next man at the South Pole of the moon in 2024. So that'll be the first time we've gone to the South Pole. All the Apollo missions were in the equatorial region. So I'll let this video play though.
50 years ago, we pioneered a path to the moon. The trail we blazed cut through the fictions of science and showed us all what was possible.
It's very pretty out here.
Today, our calling to explore is even greater. To go farther, we must be able to sustain missions of greater distance and duration. We must use the resources we find at our destinations. We must overcome radiation, isolation, gravity, and extreme environments like never before. These are the challenges we face to push the bounds of humanity. We're going to the moon to stay by 2024, and this is how.
This all starts with the ability to get larger, heavier payloads off planet and beyond Earth's gravity.
For this, we designed an entirely new rocket.
The Space Launch System. SLS will be the most powerful rocket ever developed.
And with components in production
And more in testing?
This system is capable of being the catalyst for deep space missions
we need a capsule
that can support humans from launch
through deep space and return safely back to Earth.
For this, we've built Orion.
This is NASA's next-generation human space capsule.
Using data from lunar orbiters that continue to reveal the moon's hazards and resources,
We're currently developing an entirely new approach to landing and operating on the moon.
Using our commercial partners to deliver science instruments and robotics to the surface, we are paving the way for human missions in 2024.
Our charge is to go quickly and to stay, to press our collective efforts forward with a fervor that will see us return to the moon in a manner that is wholly different than 50 years ago.
We want lunar landers that are reusable,
that can land anywhere on the lunar surface.
The simplest way to do so is to give them a platform in orbit around the moon from which to transition.
An orbiting platform to host deep space experiments and be a waypoint for human capsules. We call this lunar outpost Gateway.
The beauty of the Gateway is that it can be moved between orbits.
It will balance between the Earth and Moon's gravity,
in a position that is ideal for launching even deeper space missions.
In 2009, we learned that the moon contains millions of tons of water ice.
This ice can be extracted and purified for water. It can be separated in oxygen for breathing or hydrogen for rocket fuel.
The moon is quite uniquely suited
to prepare us and propel us to Mars and beyond.
This is what we are building.
This is what we're training for.
This we can replicate throughout the solar system.
This is the next chapter of human space exploration.
Humans are the most fragile element of this entire endeavor, and yet we go for humanity. We go to the moon and on to Mars to seek knowledge and understanding and to share it with all. We go knowing our efforts will create opportunities that cannot be foreseen. We go because we are destined to explore and see it with our own eyes. We turn towards the moon now, not as a conclusion, but as preparation, as a checkpoint toward all that lies beyond. Our greatest adventures remain ahead of us. We are going.
We're going.
We are going.
We are going. We're going.
So we've already started the Artemis program, if you will, under the CLIPS, which is the Commercial Lunar Payload Services. So we're actually 2 landers this year developed by commercial companies. I believe this year's landers are Intuitive Machines right here in JSC, and then Astro Robotics out of, I want to say, Pittsburgh. And so they are going to start paving the way for bringing commercial landers to the moon to deliver science and technology payloads for NASA, as well as commercial entities as well. You know, the Europeans are working with Nokia to put 4G on the moon for commercial communications. There's other folks who are talking about other different packages. These first missions will test out a suite of different science for NASA, from terrain relative nav, plume surfacing, interactions and whatnot. And so that paves the way with these small landers to start scouting locations, as well as just start building up that cislunar economy. Later this year, early next year, Artemis 1 will launch. And so that'll be the first Orion capsule on the SLS. It'll be uncrewed, as it's the first test flight, and it still needs some upgrades after that anyway. So that'll fly around the moon, sort of a reflight of Apollo 8 style free return mission. And then you have Artemis 2 with the first crew in a year or two. And then you start building up the gateways. So we just actually finished up the first test run on the solar electric propulsion for the gateway module just the other day. There's a video out there from Glenn Research, which oversees that actually fired up the SEP that's going to fly on the PPE. And so that gateway module allows you to aggregate for crew handover to the landers, as well as for the landers, because depending on the lander, it may not all come up in one piece. It may be 2 pieces, 3 pieces, or need refueling and whatnot. So you use that gateway as sort of an integration node between where the crew meets coming from Earth and gets on their ride, go down to the surface and stuff like that. And then you talk about larger landers to start delivering unpressurized rovers like they had on Apollo, or pressurized rovers as well down the road, where Toyota is being funded by JAXA to actually build a pressurized rover with 1,000-kilometer range, solar and fuel cell powered and stuff like that. So that'll give you a lot of traverse capability. So the gateway is that integration node. So for the initial missions, you'll have 4 people come up on the Orion capsule, 2 crew will stay on the gateway, do some outfitting and setup of that first module or 2, and then the first woman and the next man will go down to the lunar surface on the lunar lander, and they'll stay on the surface for about 1 rotation of the gateway. Because of that near rectilinear halo orbit, it has a period of about 7 days or so. So the crew takes about a day to get down on the surface, stays there for 6.5 days, and then comes back up to redock with the gateway 1 orbit later of the gateway module and stuff like that, and then do some transfers again, and then all 4 crew members leave the gateway on Orion to return back to Earth and stuff like that. So in the initial sorting missions, the stays probably won't be 30 days. It'll be less than that because of the capabilities of the lander. But then as you start building up your infrastructure on the surface, you can stay longer and stuff like that. So we do have 3 vendors out there right now developing concepts for landers, or partners as we like to call them. So it's a little different. Under the SLS and Orion, it was sort of a NASA designed, requirements down to very detailed levels, and then sort of the contractor was awarded to almost build to print that design. And in this commercial relationship we have with the partners for the lunar lander, it's more, here's your high level requirements. Take a crew of 2 to the surface of the moon, let them stay for 6.5 days, let them do several spacewalks, potentially up to 4, and then bring them back up to the gateway. And so there's a couple more requirements than that, but we kept it really high level and very limited into the number of requirements, and said, okay, industry, innovate. Tell us the best way to build a lander to get there. And so you can see from these 3 pictures, 3 very different approaches to doing the same mission of a lunar lander. And the top is Blue Origin, which leads the national team. So that's Jeff Bezos's Amazon funded Blue Origin is the descent stage. And then the ascent stage is the Lockheed Martin. So that's where the crew lives and returns back up to the gateway. And then there's a transfer stage. So they're actually a 3-element architecture. So they use a separate transfer stage by Northrop Grumman to take them from Gateway down to low lunar orbit. So that 12+ hour transit down to the low lunar orbit, about 60 miles above the moon, and then jettison that transfer stage. And then these two elements go down to the surface, and then the top piece comes back up. And then in the middle there, you have SpaceX's Starship. You may have seen they had a test flight down in Boca Chica, Texas last week in the fog. Well, actually with the fog, you probably didn't see much, but so they're cranking out those stainless steel, 50-foot tall retro style spaceships down there. Build a little, test a little, learn a lot from failures as well as success. So their lander is a lot more roomy. It has a airlock and garage there and a giant elevator to take them down to the surface and stuff like that. And then, he's talking about different starships. If you're an artist or an influencer, there's a Dear Moon project separate from NASA to fly around the moon in 2023, I think, with the Japanese billionaire there. And then in the bottom, you have Dianetics. So that's more of a very low slung, low to the ground type vehicle there, with the big solar rays pointed straight up to capture, because at the South Pole of the moon, the sun angles are very shallow, and depending on what ridges might be in the way, it's tough to get sun. And that has a very different approach. It's almost somewhat similar to a very small, like Space 1999 Eagle lander, because we've got multiple engines on it, the little engine pods on the side, and then the crew down the middle and stuff like that. So they're very low to the ground. They just have a very short ladder to get out, to get to the surface and stuff like that. And then that all goes up, so it doesn't leave anything behind. It's sort of a single stage back and forth with some refueling in orbit and stuff like that. So 3 very different approaches, and we're hoping within the next 3 weeks or so to make the announcement of which 1 or 2 teams will be then get the contract to race towards that 2024 mission. It's not clear yet. Will one team be picked for 24 and one for 2025, or how that'll all work? We still have to work with the vendors, their schedules, the funding we got from Congress, and whatever the new president's direction is and what milestones and schedule he wants to work towards and all that. So the South Pole of the moon is very unique. As we said, we have permanently shadowed craters there, which mean there's water ice in those permanently shadowed craters that have never seen sunlight. But then you also have high ridges, which are eternally in sunlight, so that you could have those for power if you didn't have nuclear power there. So there's the balance between the two there. At the equator, where you were with the Apollo missions, you had 14 days of sunlight, but then you had 14 days of darkness. And so it's tough to build a spacecraft that has to survive the lunar night. So depending on where you are at the South Pole, you can be in more of a somewhat twilight all the time, if you will, versus having to deal with a long lunar night and stuff like that. And so it's a good test ground on the South Pole to, we'll do a couple sortie missions to check out the South Pole with these 2 crews living in the lander, find some science and interesting locations, and then start talking about potentially long-term building up a permanent lunar base there. The plan was in 2028, you'd start building up a lunar base, start looking for all those unknown unknowns you have to find before you commit to a Mars mission in terms of expeditionary logistics. How many spares do you need to bring versus how much parts do you feel comfortable you can 3D print out replacements in your habitat with, versus having to always have to have new pumps and supplies. How much of that ISRU, in situ resource utilization, you can do in terms of mining the water ice, turning it into clean water for drinking, or oxygen to breathe, or hydrogen and oxygen to refuel your landers and stuff like that. And obviously radiation protection. There's no atmosphere on the moon, so you need to know about how you can protect the crew, whether it's lava tubes for where they can shelter in, or habitats covered in several feet of lunar regolith to protect you from radiation. Growing plants, vegetables, lab grown meats is a coming thing here on Earth. Is that something to help supplement their freeze-dried food on the moon? And then you start thinking about Mars, what the lessons you learn on the moon help lean forward for Mars, because there you're committing to a 1,000-day plus mission, where you've got 200 days transit out there, 500 days on the surface, and then another 200 plus days back. So the moon lights the way to Mars. But if we're talking about going out further, some of the technologies we work at here at JSC, life support, active thermal, entry, descent, and landing. So the rover that just landed on Mars was built and designed and worked out of JPL, but we did help with some of the entry, descent, and landing and analysis for flight mechanics. So there, avionics, human system up interfaces, wearables, RFID tracking for logistics. So we've got a project on the space station where, you know, you got a crew that's rotating every, 6 months up there. There's bags everywhere. Where did the last guy leave the hammer? Well, he's down on Earth now, and he doesn't remember where he left it. So if you use RFID tracking, you can help find all that. Different structures and habitats in terms of inflatable, expandable. They're very particular about that. They call it expandable because if you say inflatable, you think about popping and all that. So because you're limited by the launch fairing of the rocket. So if you have a 3-meter launch fairing, but then you can expand out to 5 meters, that's a lot more volume and stretch out, the other axis as well. And then power and propulsion, and I've got some slides on that we'll get into. And then software, again, there's Robonaut and simulations and whatnot. So the big challenges, again, for getting to Mars is it takes so long to get there right now. Again, you're talking 1,000-day mission round trip because it takes 200+ days to get there. Because of the orbital dynamics, you only have a launch window every 22 months. Then you have to stay for 500 days and then come back. Or if you only stay for 30 days because you're doing a leave when the planets are not aligned and you're getting there, you only have 30 days to stay. Then you have to swing by Venus either on the way out or the way back to get back to Earth and stuff like that. And then getting to the surface is hard. The rover we just landed is only 1 ton to the surface. When you start talking about human habitats and pressurized rovers, you're talking 5 tons for a rover, 10 tons to potentially up to 40 tons in logistics you need to drop down for a human surface hab and all the supplies there. So we've never done anything that big before. So we need new technologies for getting down to the surface. You can't just do a parachute because the atmosphere of Mars is too thin to really help out, but just thick enough to be a pain in the butt. So you have to really balance out how you get down there. The smaller spacecraft can get down there with parachutes, and then the inflatable balloons that they put around it, like the first rovers, like Sojourner and stuff like that, whereas that tripod of airbags around it and sort of just bounced on the surface. With Curiosity and Perseverance, it had the sky crane with the retro rockets, and then lowered it down on a wire system. But then for something like as big as a Habitat or a big pressurized rover for humans, you need something new, supersonic retro propulsion and something else to get down on the surface. And then living on Mars is not going to be easy. So there's that supply chain again. Now you have a launch window that's only every 22 months. You have 250 days to get there. So if something breaks, you can't be calling the home for help. You can't know that your next supply of food or oxygen is on the launch pad and still has 2 months before the launch window opens, stuff like that. So you have to live off the land as much as possible. And, or you speed up and get there faster. So there's a lot of technology gaps. That biggest one for NASA is probably faster and more efficient propulsion, radiation protection from the crew, as well as the systems on board. There was an alarm on the Crew Dragon just last week. They think it was a single event upset in one of the computers. And so when the system rebooted, it sent a spurious signal to the ISS, and the ISS interpreted that spurious signal as, I think, a fire smoke event. And so, that's kind of a big deal to have a fire in space. So it was just a false alarm, but you get radiation events using especially commercial off-the-shelf parts and stuff like that. That's something to think about. The crew issues for microgravity and long duration. That's why we've learned a lot with the ISS, with crews living for 6 months in a year, all that muscle mass and bone loss that they have, how to keep them. The crew on the ISS exercises 2 hours a day, 6 days a week. Who has time or gym membership for that here on Earth? But it's necessary for the space station to keep that up, because they were coming back on those first few ISS missions. We thought we understood what happened in the human body after, years of flying the space shuttle, for 2 weeks at a time and stuff like that. But those first few crews coming back after 6 months, I mean, it took a long time for them to recover and stuff like that. Some of the astronauts, mostly male of European descent, have interocular pressure. Their fluid shift causes a change in their vision. So you want to better understand that, so that you don't, when you get to Mars, you want to be able to walk and see, so you have to learn those lessons, or again, you get there faster and you don't have that problem. The large entry, descent, and landing, you can test that out. Closed loop life support. Again, the ISS is not fully closed loop. It's about 87% closed loop. So we still have the supplies every so often of water and oxygen coming up on the cargo missions and whatnot. But again, the further you go out there, the longer that supply chain is and the longer it takes to get resupply. Power on the moon, there are areas of, eternal sunlight, but there are also areas that, you're going to want to explore that have 14 nights in a row. And so you want to talk about nuclear power, pre-positioning fuel cell rechargers or something like that. And then when you go out to Mars, you've got dust storms that interfere with solar power parts of the year. So you can't really just rely on solar power unless you have a huge solar array farm that can handle even, the minimum power levels you're going to get out of it during a dust storm. So the other option is nuclear surface power or beaming power from space down. That's another way. Spacesuits in a dusty environment. If you've ever seen the pictures from the Apollo era, Gene Cernan sitting in the Apollo 17 capsule, just white suit covered in Apollo dust, stuff like that. So if you're talking about 500 days surface mission, that's probably 1 or 2 spacewalks a week for, a year and a half. That's a lot of wear and tear on that suit. The regolith on the moon is sharp, glassy, and really abrasive because there's no wind to smooth things out. On Mars, it's not as, cutting, but it's still, after 500 days, is going to get into your gears and stuff like that and gunk up the works. High-speed data communication, on Mars, you're talking 8 minutes, 20 minutes, depending on the orbits, of one-way comm delays. So you can't have a critical failure and say, help, and then wait 20 minutes for somebody to get the answer. Think about the situation for 5 minutes, make a call back. Well, it's almost, 45 plus minutes later, your help is probably dead by that point. So you need AI or mission control in a box to help get you through some of those critical situations. And then robot caretakers, set up your base before you get there. Make sure that the ascent vehicle is fully fueled up and ready to go, that all the pieces of the hab are put together, that all the tires are and the oil changed in your rover and ready to go for that. And then again, that 3D printing for your expeditionary logistics and stuff. So I know you guys are nuclear, so I gave some high level stuff here. None of this stuff is done here at the Johnson Space Center. So, this is cursory level knowledge. I don't want any hard hitting questions on any of these charts from now on, but we do have Hall thrusters that we've been flying. The Dawn spacecraft went out to Ceres and Vesta, which are dwarf planets. That's managed out of the Glenn Research Center up in Ohio. So those Hall thrusters, they're working on next generation Hall thrusters, and that's basically what the gateway PPE, the power and propulsion element. So that has a 50 kilowatt solar electric propulsion. It's being built by Maxar, and just had a test yesterday. I probably should have put a link in here, but I'll update these charts, and Steve has the link. He can pass them along. But so that's the next generation Hall thruster engines that'll allow you to do those small micro changes in orbit to keep you in that near rectilinear halo orbit. Vasmir is a spin-off company. Former astronaut at the ISS has talked about his specific impulse magnetoplasma rocket. I think you probably guys have heard this, has studied it with plasma stuff you've done. There's been talk over the years of potential test flight on the ISS, that because the ISS has those big solar arrays, you could potentially power up the Vasmir rocket there and do it for some small impulses instead of having to use chemical propulsion from one of the Soyuz or the cargo Progress to do a reboost of the station. You could use the Vasmir to do any of those orbital boost maneuvers and stuff like that. So that's something. And Vasmir, if it comes out as a technology breakthrough, I think, if you have the right power source and a large enough engine, you're talking cutting down the Mars trip from 250 days to 40 days. So you get down there in 40 days, then you're talking expanse level Epstein drive, where you're not worried about your logistics or your radiation or your microgravity concerns as much, because you're zipping there. You'll do a burn halfway, flip and burn to slow down the rest of the way, and you get there in a fast enough time that your body hasn't had as much radiation impact, or you can get supplies faster, so you don't have to have maybe drop 40 metric tons of food and water and oxygen in one. You can just do more supply runs because you don't have that 22-month launch window, because you've got the a faster rocket that can go on a non-Hohmann transfer. Nuclear propulsion is another big one. We collaborate with the Department of Energy for that. And that's managed out of the Marshall Space Flight Center. That's in Alabama. And so they've done several things with Los Alamos and the Idaho National Lab as well. Some demonstrations. So there's two flavors of nuclear propulsion we're looking at: nuclear electric. So basically beefing up a Hall thruster or something. So instead of solar electric propulsion, it's nuclear electric propulsion. So it's the same type of thruster, similar to the Hall thruster, just with the nuclear power to really crank up the speed there. So you're talking 40 kilowatts to 2 megawatts of power there. Or nuclear thermal, where you're flowing hydrogen over a nuclear reactor, and the heat from the reactor is vaporizing the hydrogen, and that's what you're expelling out the back end is your ejecta. And so you have high-speed gas, and that gives you a higher specific impulse. So if you look at, the space shuttle main engines had a specific impulse of 450 seconds. A potential nuclear thermal is 900 seconds. So that's sort of like your miles per gallon type, efficiency of the engine. And so that's on the low side of what a nuclear thermal could be. So again, anything that gets you there faster helps make you have a more sustainable, robust surface operation, because you don't have to have a rigid supply chain, because you can get there more often and quicker. There's a little about, I assume you guys know about nuclear thermal propulsion, but it's a quick video just showing how you've got the water or hydrogen just floated around the reactor, and then that fission in the reactor just generates heat, and then vaporize the hydrogen to then flow out the back at high speed. That's actually an Idaho National Lab, I think, video. So once you start talking about getting to the surface again, on the moon, there are areas of, 14 days of darkness. On Mars, you've got dust storms and you're further away, so the solar power efficiency isn't as great. So you want to start talking about kilowatt power in terms of nuclear power. So again, this is a project out of Glenn. They actually tested Krusty, and now they're building up a version to actually fly to the moon as a test bed. And so it'll be potentially 10 kilowatts of electric power that can run for 10 years. So that would be a great effort for the bigger the base you have, that with 10 kilowatts of power or multiples of these, you can build up a better base without having to rely on solar arrays and dust storms and all that.
We design
So, and then there's already nuclear roving around on Mars right now. The RTGs, it's the next generation RTGs that are running in Perseverance and Curiosity. So this is it's a low power in terms of it wouldn't be sustainable for human missions because it's only in the 100 of watts range, but it's a small radiothermal electric isotope generators there. So it's got the core there, and then it heats up, and due to thermoelectric, you generate power and heat for the keeping alive the rover and whatnot. So there's actually two nuclear RTGs on the Mars right now. There was one on Cassini as well. I believe Juno has one. So the further you go out, you have to start depending on RTGs, just because the solar power past Mars doesn't really buy you much unless you have a really big solar array or a concentrator where you had an inflatable sort of concentrator then onto a smaller solar array farm and stuff like that is one way to do it. So radiation testing, I did talk about that a little bit. So at Goddard Space Flight Center, they do a lot of testing, as well as some other test facilities around the country. We just had a briefing the other day for the Lunar Lander program, where there's maybe 39 facilities that can do different, high powered radiation, high heavy ion type testing for your electronics and stuff like that. And it's a big issue, because if you start going to these commercial products, they're not built for going into space. They don't think about that when they do board layout and how ion goes through the board and causes your disruption, single event upsets, or locks up a field programmable gate or something like that. So we have to do all these testing, and there's not as many facilities as we'd like with enough test time during the year to really crank through what a spacecraft could need in terms of all the COTS products it's using and stuff like that. And there's not really a lot that's been advanced. I think some of these spacecraft are still running 486 level, chips, because that was the last generation, or Pentium. That was the last generation that was rad hardened, that the military paid for rad hardening on to really be able to be used in space and stuff like that. So we're sort of at the whim of some of those limitations. And then for the crew, we do think about radiation crew here. We do have the space weather group that is always watching the sun for solar activities, stuff like that. For Orion, there's a little hole in the floor that they can sort of take bags out of from storage, and all of the crew sort of, if there is an event during their transit time and whatnot, would sort of hunker down in that whole area and put as many bags and everything over it. And so you just had as much mass between you and the solar particles to try to protect the crew and stuff like that. So it is a concern for the astronauts. And again, the further you go out there, the more time you're in that radiation environment from cosmic galactic rays, or just the radiation from potential solar flares and stuff like that. So we have to think about that. We don't have the magnetic bubble to help us, though there was a paper, I guess we would call it a white paper, that headquarters, some other folks put out a couple years back, where you could put a 2 Tesla range magnetic bubble station at the Sun Mars Lagrange point. So it was in between the sun's here, the magnetic space stations here, and Mars here. So we create this magnetic bubble here, which would protect you from the solar wind and solar radiation, because the magnetic bubble there would put the planet always in its magnetic wake and stuff like that, so that any radiation from the sun would sort of go around the planet and stuff like that. And it's doable, but it would take a lot of mass and power to create this magnetic bubble there, that space station at that Lagrange point between the sun and Mars, to then protect the planet from some of the radiation, but not necessarily all of the radiation.
It's August 1972, and Ian Richardson, a future NASA scientist, is watching TV when the BBC...
So that was my last chart. I don't know how we're doing questions here, Steve, or what the forward plan is. Or did I only run over time?
So yeah, I think we probably still could take some time for
I have time, so it's up to you guys.
So I'm sure we have time for some questions. I know we are over a little bit, so I do understand if people need to leave early, but I definitely want to take some time for some questions. So the way it usually works, or the way it's worked previously, is same thing holds here, is either raise your hand and I'll call on you, and we'll try to do that in order. Or please post your questions onto the chat, and I will I can read them off. So our first, we got one question from one of our attendees, Josh. You want to go ahead and unmute and ask your question?
Yes. Thank you very much for the talk. It was interesting to hear a little bit of everything going on right now, not only at Johnson Space Center, but around the rest of the different centers. So from an operations standpoint, when it comes to these sort of down select periods from the white paper stage to the mock-up stage, and then the down select of these human landing systems, what are the challenges involved in studying the operations of those separate vehicles and how they would then interact with the ascent stage and with the gateway?
So I haven't been on the source board for the down select so far. So I know they get a really detailed package from each of the companies in terms of, they're given the requirements and all this other stuff. And you can actually go out to FedBizOps and look up Appendix H, the call for NASA, and see what information we passed over to them in terms of safety, operational constraints, construction standards that they had to meet. Again, the high level 20 or so requirements you gave them. So they were given a detailed package of, okay, you need to cover all these areas in your bid. And then from what I understand, being an outsider to the source selection board, is the team will take the bid in, look through their proposal, make sure it's meeting those requirements, meets or exceeds, or an area of risk and all that. Is there something that they didn't think about? There's an internal NASA design reference mission that we sort of helped scope, and a mission timeline that we helped develop, and some other tools that I think the source board had access to say, here's a sanity check on our lander is a 3-element, totally different than any one of these vendors' proposals, but at least takes in these operational considerations. Here's gaps we showed that the timeline doesn't work unless you add an extra cruise leap here or something like that, because this transit time is longer than we anticipate with our design and stuff like that. So I think they have to trade all that, and they look at, I don't think they compare vendor to vendor specifically. I think they compare the vendor's bid proposal against what the requirements in App H were, and then from there do the ratings and scoring, stuff like that. But again, I'm not part of the source board, so but I know a lot of that goes into the discussions in terms of just trying to evaluate and make sure that they are getting it. And then in this baseline period, we did talk about, we had meetings with the different vendors over the last year since the 3 were selected, those 3 partners, and we helped go through and better understand their design and talk about different things, and they helped understand what some of the constraints and gaps were and stuff like that. So it's been a partnership for the last year, but now they put in their final bids, and we'll see what happens.
Awesome. Thank you.
Dr. Hayes, you got a question?
Yes. Does NASA consider nuclear energy to be green, and why or why not?
As far as I know, I think they do. I think they consider it for meeting our needs. It's a green technology in terms of it allows them a more capable power package than the solar power that you have to deal with in terms of sunlight, dust, different times of the year, different power levels, degradation of the solar cells over time. It's a more consistent power from NASA's standpoint. I don't know that there's an official position that this is a green technology versus, a non-green technology. I don't know from an agency standpoint. It's not like we have to deal with the nuclear waste of these, because it's a compact, self-contained reactor that's good for 10 years of use, and then it just sort of is retired in place. I think it's different reactors than you're talking about the big reactors here on Earth and stuff. But I know they're, some of the companies are working on smaller, scale reactors that could be deployed, in a trailer and stuff like that are more self-contained for remote operations here on Earth or evacuation scenarios, stuff like that. So do you consider it green, I guess, from the way NASA's using it?
Well, I consider it green in the sense that if geothermal is green, then nuclear is, right? They're the same energy source.
Right.
And thorium, 14 billion year half-life, it'll be around even after the sun goes red giant in 5 billion years. So in a sense, it's even more renewable, has long-term stability and sustainability in that sense. That'd be my opinion.
I think the biggest struggle we have is, depending on where it's used, is it in a microgravity environment? So that's a lot different operation, because you have the fluids moving around for cooling and stuff like that. You have to take into account that it's not like you could take a nuclear reactor design that works fine here on Earth in 1G with, a regular gravity vector and pumps and fluids, and just take it and put it on the space station. There's different considerations there. Now, do all the 1G reactors with that similar design work fine on the moon in 1/6 gravity, or on Mars in 1/3 gravity? We don't know yet. And I think that's where Kilowatt Power is trying to get to, is to see if they can design something here on Earth that works fine and is capable for providing 10 kilowatts of power in the moon in 1/6 gravity.
We got a question from one of our participants, Naaman. If you want to unmute and ask your question.
Yep. Thank you, sir, for the great talk. It's exciting to see what the future looks like at NASA and for the space industry. My question is kind of a general one for students like me, and most of us are here, graduate students. What's your advice on kind of how to get into the space industry, or if you want to work at NASA, what's your overall advice? What should we if you're graduating in the next year or a couple of years, what should we focus on, and how can we just kind of get our foot in the door?
Sure. So these days we're kind of under not a hiring freeze, but it's very constrained. And the internship pathways for both undergrad and graduate is the best way to get your foot in the door while you're still in school. You come for a semester, work here, and then go back to school for a semester. And so you do several rotations like that. There's graduate programs as well that can work with you, come here for the summer and stuff. That's where typically a lot of our hiring as a NASA civil servant comes from, but there's also the contractor route. We have a good relationship. It's somewhat of a badgeless society. We try to say here where, everything doesn't matter if you're work for Jacobs or NASA, you can do the same job. It's only certain levels of program managers, stuff like that, that are civil servant jobs, stuff like that. So that's an easier route. Typically for NASA, you do have to be a US citizen, though there are some exceptions to that. I believe Ames has some foreign nationals, and some other centers do have some agreements. And then obviously here at the Johnson Space Center, since we have the International Space Station program, there's, support from all the different companies, in terms of the international partners. So you've got, folks from Japan that work for JAXA and stuff like that. So there's opportunities as well if you're not a US citizen for it, but for the most part, as federal employees, you're US citizens, and as well as for some of the contractors due to ITAR and stuff like that. But the intern.nasa.gov has all the calls of how to apply the different programs for undergraduate and graduate. And that's really, as an entry level, that's the way to get your foot in the door, unless you're what's called a critical hire. So you have to have a very unique skill that's missing, and that the center is trying to build up that capability in and stuff like that. And so usajobs.gov is the other way you can look at different calls for opportunities to apply for NASA or anywhere within the federal government and stuff like that. So it's not as easy as it used to be in terms of getting hired. Back when I started, obviously volunteer was a way outside the door case, but you didn't have to come up through the internship. You could get hired in off the street as a flight controller or elsewhere at JSC. But now, because of some of the constraints in terms of hiring limits and number of workers per center, it's mostly the Pathways internship program is the way to sort of get tested out, and so that instead of cold hiring you, they've seen you for several semesters to get an idea of what your capabilities are, whether or not you're a good fit, whether you like doing the work. It's kind of a good way for you to sort of test out working for NASA. Is it really the place you want to be, or do you want to work for some of the commercial companies?
So to that point, by the way, so most of you might have seen it today. Ms. Bailey sent out an email with the internship application through NASA. I think Dr. Bolinoff had passed it along to her. And and one thing to take a look at there is there's a list of specific designated projects where they're trying to find interns and co-ops to work on at the graduate level. But you definitely want to go through those and see if there's anything that's a fit for any area of technology you're working on in school, and apply to those. It's important not to. It's like anytime you're applying for a job, you got to make sure that there's a fit. But I think there's probably about a dozen pages of different project titles that are in that link that Ms. Bailey sent that you should take a look at.
Yeah, and that's why I try to identify a little bit in which areas and which centers are working on the different nuclear propulsion, stuff like that. Glenn, Marshall, those are the big ones playing these days. So look at opportunities at those centers just to see what internships would be there. Nuclear here at JSC, we just don't do anything with that. It's fuel cells and managing the solar arrays somewhat on the space station, but even that solar array power is super managed out of Glenn.
I think most of the plasma work is also out of Glenn. Most of the people I knew out of Michigan who went to work for NASA, I think they ended up they started off at Glenn at least. We have a question on the chat from one of our attendees. You mentioned SCUs. What role do you think safety and probabilistic risk analysis play at JSC at the different divisions that you mentioned?
So yeah, so there's always a PRA analysis before any hardware flies to the space station or before anything flies on Orion or Gateway or the lander. So there'll be a safety risk review. Radiation testing will have to have been done on that beforehand and stuff like that. And then that'll play into what the ops team has for their contingency scenarios, their responses. You know, does a single event upset cause, you know, false flag that the crew can quickly ignore and save the system, or is it something that they need to get in there and hard reset something and stuff like that? So it's a synergy between the analysis that's done pre-mission or pre-launch on that, and then what the safety officer's assessment is of that risk, and then how the engineering team and the operations team feel the workarounds or reconfiguration or reestablishment of the after the single event upset is. So it's a team effort to work through that risk assessment and then what the turnaround and reconfiguration is.
I mentioned PRA would play a bigger role when you mentioned something going wrong on a Mars mission where you can't necessarily get that'd be a big part of that mission control in a box, right?
Yeah, so you have to think about, you know, through your testing, you know, whether it's board level testing, radiation testing, or just, you know, integrated testing with the vehicle and stuff like that. What are your failure modes? What is the fallbacks? Is it a watchdog timer that, you know, wait, if that kicks off, then you just go into a safe mode and wait for the next uplink from the ground to look at the problem and send happy words? Or does the mission control, especially for a rover, does it see something it doesn't like and have enough self-awareness to, I'm not going to drive off this cliff, but that, you know, mission control didn't know about because the last pass was obstructed here and didn't see that there was a, you know, new crevasse had opened up or something due to a Mars quake, you know. So it's how much autonomy the system has on board to handle some of those off-nominal situations, or is it just hold and wait for the ground to clear it up? Or, you know, if you're talking about a human mission, how much does the crew training play into that? How much independence do they have and autonomy to say, okay, we're going to do a reconfiguration because we understand the problem is this? Because again, with those comm delays, they might not be able to wait up to an hour, you know, with two-way comm and the crew asking the question, mission control thinking about it and getting an answer right back. You know, it's not going to be instantaneous anymore. You know, you've got less than a second delay at the moon, you know, or up to 2 seconds. But then when you get out to Mars, you're talking 20 plus minutes each way. So you have to have that. What is that level of autonomy in the software versus in the crew versus in just, you know, the training and just the awareness of how to handle some of those problems, because you've done enough integrated testing and risk analysis beforehand to know what the potential problem is and what the right outcomes are going to be.
Thank you. So I don't see any other questions coming up on the participant list. No one's hand is up or on the chat. If there is any other questions, I'll give a quick countdown to see if anyone else has any questions. But barring any other questions, I definitely, obviously, it's always good seeing you, Mike, and want to thank you for a really nice presentation and some insight into how things work at NASA. It was really interesting hearing about the thing that jumped out at me was the he mentioned some of the kind of archaic technology. NASA's a lot like nuclear energy in the sense that it seems like you don't necessarily get to work with the most cutting edge. You got to work with what you know, what you know is rock solid in operation. Nuclear kind of has the same thing, where I think a lot of times it isn't as fast moving as other industries. It's interesting that, you know, for two perceived as extremely cutting edge,
yeah,
that actually so much of it relies on so much of our systems rely on what actually is in a lot of cases not necessarily the cutting edge for our fields. It's interesting.
Yeah, so when they were building up Mission Control back in the day, you know, Gene Kranz realized that computer technology, mainframes were going to advance, but they couldn't keep, you know, chasing that upgrade cycle of computers, and they had to just pick Mission Control, the IBM 4 kilobits of RAM or whatever it was, you know, computers, and rely on the flight control team to handle that, you know, gap in computer power with training and the number of people and eyeballs thrown at the problem. You know, if you talk about something that flies on the space station, if it's flight critical hardware, you know, it may take several years or more to get on the space station, to get built up, go through all its testing, all its risk analysis, all its, you know, operational constraints and all that, that by the time it flies, it's, you know, already outdated in terms of the high tech components inside. But you can't keep chasing that, or you have to take that more risk if you fly more COTS off the shelf in terms of trying to get it up there in an expeditious manner. You run that risk of, because it's not made for space, it doesn't have some of those protections from radiation and the thermal environment and, you know, the pressures and stuff like that, that you have to think about it. And so either you have to heavily test it as quickly as possible, or you just accept that as a known risk going in. That, you know, the laptops, I think, were finally upgraded, I want to say, to off of XP to, you know, Windows 10 or something like that finally. But, you know, there's like 200 or so laptops on the space station and stuff like that. They're not critical. I mean, over time, they've taken on a more critical nature, but, you know, they're more powerful than the main computer brains of the space station. But, you know, they always have to deal with the computers there, because that was like the last ruggedized version for the longest time. And now they've just upgraded them to, I don't even know what processors flying in the laptops, but it's not the latest, you know, one you'd be playing your games on that you got at Best Buy.
Sure. Well, our department IT guy, I think, would probably have a stroke if he worked at NASA, because
well, our work computers are not, you know, cutting edge and stuff like that. I mean, they're on a 3+ year refresh cycle, so
right.
they're not chasing the latest greatest.
Well, thank you again, and hopefully I get a chance to come down and visit you sometime in Houston again. But
Sure.
With that, I want to go ahead and thank you, and thank everyone else for being here, and look forward to seeing everyone at next week's department seminar. And everyone have a safe week, and look forward to seeing you soon. So thank you very much.
Thanks, Steve.
Thanks a lot, Mike. Appreciate it.
Have a good day.